Welcome back to our course, Networks and Distributed Systems, based on the textbook Computer Networking, a Top-Down Approach by Jim Caros and Keith Ross. We have already discussed the application layer and the transport layer of the TCP/IP model. Most recently, we have been investigating the network layer of the TCP/IP model. Our most recent lesson had to do with the conversion from IPv4 to IPv6 for addressing in the network layer. Now we're going to pick up with a discussion of the interplay between routing and forwarding. So let's pick up where we left off. So far in this unit, we've mostly explored the network layer's forwarding function. We learned that when a packet arrives to a router, the router indexes a forwarding table and determines the link interface to which the packet is to be directed. We also learned that routing algorithms operating in network routers exchange and compute the information that is used to configure these forwarding tables. Having explored forwarding in some depth, we turn our attention to the other major topic of this module, namely the network layer's critical routing function. Whether the network layer provides datagram service in which the different packets may take different routes from source to destination, or a virtual service where all the packets between a given source and destination will take the same path, the network layer must nevertheless determine the path that packets take from senders to receivers. We'll see that the job of routing is to determine good paths from senders to receivers through the network of routers. Typically, a host is directly attached to one router, the default router for the host, also called the first hop router for the host. Whenever a host sends a packet, the packet is transferred to its default router. We refer to the default router of the source host as the source router and the default router of the destination host as the destination router. The problem of routing a packet from source host to destination host clearly boils down to the problem of routing a packet from source router to destination router, which is the focus of this section. The purpose of a routing algorithm is simple. Given a set of routers, with links connecting the routers, a routing algorithm finds a good path from source router to destination router. Typically, a good path is one that has the least cost. We'll see, though, that in practice, real-world concerns such as policy issues also come into play to complicate the conceptually simple and elegant algorithms whose theory underlies the practice of routing in today's networks. A graph is used to formulate routing problems. Recall that a graph, such as this one, G equals open paren N, comma E, close paren, is a set of nodes, represented by the N, and a collection of edges, represented by the E, where each edge is a pair of nodes in the set. In the context of network layer routing, the nodes in the graph represent routers, the points at which packet forwarding decisions are made, and the edges connecting these nodes represent the physical links between those routers. Such a graph abstract of a computer network is shown here. As shown here, an edge also has a value representing its cost. Typically, an edge's cost may reflect the physical length of the corresponding link. For example, the transoceanic link might be higher cost than a short-haul terrestrial link. Could be the link speed or the monetary cost associated with the link. For our purposes, we'll just simply take the edge cost as a given and not worry about how they are determined. For any edge in a set of links, we denote C open paren X comma Y close paren as the cost of the edge C between the nodes X and Y. If the pair X and Y does not belong to a set, we'll just set that pair cost to infinity. Also, throughout, we consider only undirected graphs, that is, graphs whose edges do not have a direction. So that the edge open paren x comma y is the same as the edge open paren y comma x. And that the cost of x comma y is exactly the same as the cost of y comma x. Also, a node y is said to be a neighbor of node x if x and y belong to the same set. Given that the costs are assigned to various edges in the graph abstraction, a natural goal of a routing algorithm is to identify the least costly paths between sources and destinations. Given any two nodes, such as x and y, typically there are many paths between the two nodes, with each path having a cost. One or more of these paths is a least cost path. The least cost problem is therefore clear. Find a path between the source and the destination that has the least cost. In this figure, for example, the least cost path between source node U and destination node W is U to X to Y to W with a path cost of 3. U to X 1, X to Y 1, and Y to W 1. Note that if all edges in the graph have the same cost, the least cost path is also the shortest path. That is the path with the smallest number of links between the source and the destination. As a simple exercise, try finding the least cost path from U to Z in this figure, and reflect for a moment on how you calculated that path. You found the path from U to Z by examining the figure, tracing a few routes from U to Z, and somehow convincing yourself that the path you had chosen had the least cost among all possible paths. Did you actually check all 17 possible paths between U and Z? Probably not. Such a calculation is an example of a centralized routing algorithm. The routing algorithm was run in one location, your brain, with complete information about the network. Broadly, one way in which we can classify routing algorithms is according to whether they are global or decentralized. A global routing algorithm computes the least cost path between a source and destination using complete global knowledge about the network. That is, the algorithm takes the connectivity between all nodes and all link costs as inputs. This requires that the algorithm somehow obtain this information before the calculation. The calculation itself can be run at one site, a centralized global routing algorithm, or replicated at multiple sites. The key distinguishing feature here, however, is that a global algorithm has complete information about connectivity and link costs. In practice, algorithms with global state information are referred to as link state algorithms, since the algorithms must be aware of the cost of each link in the network. In a decentralized routing algorithm, the calculation of the least cost path is carried out in an iterative, distributed manner. No mode has complete information about all the cost of all the network links. Instead, each node begins with only the knowledge of the cost of its own directly attached links. Then, through an iterative process of calculation and exchange of information with its neighboring nodes, a node gradually calculates the least cost path to a destination or a set of destinations. The decentralized routing algorithm we'll study is called distance vector algorithm because each node maintains a vector of estimates of the costs, that is distances, to all of the nodes in the network. A second broad way to classify routing algorithms is according to whether they are static or dynamic. In static routing algorithms, routes change very slowly over time, often by human intervention, such as a human manually editing a routing's forwarding table. Dynamic routing algorithms change the routing paths as the network traffic loads or topology change. A dynamic algorithm can be run either periodically or in direct response to topology or link cost changes. While dynamic algorithms are more responsive to network changes, they are also more susceptible to problems, such as routing loops and oscillation in routes. A third way to classify routing algorithms is according to whether they are load sensitive or load insensitive. In a load sensitive algorithm, link costs vary dynamically to reflect the current level of congestion in the underlying link. If a high cost is associated with a link that is currently congested, a routing algorithm will tend to choose routes around such a congested link. While early ARPANET routing algorithms were load sensitive, several problems were encountered. Today's Internet routing algorithms such as RIP, OSPF, and BGP are load insensitive, as a link's cost does not explicitly reflect its current or recent past level of congestions. Well, we're about to get into some detail about link state routing and distance vector routing. So before we do that, this is a good place to take a break. Review your notes, take a look at the videos and spots if you missed something. Update your study guide. And when you're ready, come on back and we'll proceed to the next one.